Right now, on a mountain in Chile, a machine the size of a small car is opening its eye every 40 seconds and capturing more of the universe in a single night than most telescopes capture in a year. It is not looking for one thing. It is looking for everything. Every asteroid drifting through our solar system that no human has ever seen. Every star that flickers or explodes. Every galaxy hiding at the edge of visible space. And in the last few months, it has started finding things so fast that the scientists running it can barely keep up with their own data. Nearly 1 million alerts in a single night, over 11,000 new asteroids in under 2 months. A camera so large and so sensitive that a single image from it would need 400 ultra-high-definition televisions stacked together just to view it at full resolution. This is the Vera C. Rubin Observatory, and what it has just done is not a minor technical milestone. It is the beginning of something that professional astronomers have been waiting for their entire careers. And here is the part almost nobody is talking about clearly enough. This observatory is not just going to discover new objects in space. It is built to hunt down one of the biggest unsolved mysteries in all of physics, a substance that makes up most of the matter in the universe, and that no human being has ever directly seen, touched, or detected in a laboratory. Stay with me, because by the end of this, you are going to understand exactly why scientists are calling this the most important astronomical machine built in a generation, and why the woman this observatory is named after had to fight for decades just to be allowed near a telescope at all. If stories like this are the kind of thing you want more of, go ahead and subscribe now, because we are only getting started. Let's start with the basics, because the scale of this thing is genuinely difficult to hold in your head the first time you hear the numbers. The Vera C. Rubin Observatory sits at the top of Cerro Pachón, a mountain peak in northern Chile, roughly 8,800 feet above sea level. The site was chosen because the air there is dry, the skies are dark, and the atmosphere is unusually stable, which means less shimmer, less distortion, and a clearer path for light that has been traveling for millions or even billions of years before it finally reaches a mirror built by human beings. That mirror is 8.4 meters across, and paired with it is the largest digital camera ever constructed for astronomy, a camera with 3,200 megapixels. To put that in perspective, a high-end smartphone camera today might capture 50 megapixels in a single photo. This camera captures 64 times that in one exposure. Each image it takes covers a patch of sky equivalent to 45 full moons side by side. The camera itself weighs as much as a small car and required specialized optics ground, with a precision measured in nanometers. Every single night that this observatory operates, it takes around 1,000 images, and every single one of those images generates roughly 20 terabytes of raw data. Over the 10 years of its planned survey, scientists expect it to produce more than 500 petabytes of information, enough data that if you tried to store it as printed photographs and stacked them, the pile would rise for miles into the sky. And the entire reason this machine was built, the actual scientific purpose behind an instrument this expensive and this precise, comes down to a project called the Legacy Survey of Space and Time, an attempt to photograph the same patch of the southern sky over and over again for a full decade, creating what scientists have started calling the greatest time-lapse movie of the universe ever made. But before we go further into what this observatory is doing right now, in the summer of 2026, we need to go back to where this story actually begins, because the name on this building is not a marketing choice. It belongs to a real woman who spent her entire career fighting to be taken seriously in a field that did not want her there, and whose discovery is the exact reason this observatory exists in the first place. Vera Rubin was born in 1928, and from an early age she was obsessed with the night sky. As a child, she used to lie awake watching stars pass by her bedroom window, tracking their movement for hours simply because she found it beautiful. When she applied to Princeton's graduate astronomy program in the 1940s, the university would not even send her their course catalog because, at the time, women were not admitted into the graduate astronomy program at all. She went elsewhere, earned her degrees anyway, and by the 1960s, found herself working alongside an instrument-building physicist named Kent Ford, who had developed one of the most sensitive spectrographs of its era. Together, they turned their attention toward a question that most astronomers at the time considered basically settled. How fast do stars orbit around the center of a galaxy? The expected answer, based on everything Newton and Kepler had taught astronomers for centuries, was simple. Stars closer to the center should orbit faster, and stars farther out should orbit slower, the same way planets farther from the sun move more slowly than planets close to it. Rubin and Ford pointed their spectrograph at the Andromeda Galaxy and started measuring. And what they found did not match the prediction at all. The stars in the outer edges of the galaxy were moving just as fast as the stars near the center. Not slower, just as fast. Fast enough that, according to the laws of gravity as they were understood at the time, those outer stars should have been flung off into space entirely. The galaxy should not have been able to hold itself together. But it was holding together. Something invisible, something that gave off no light and could not be seen through any telescope on Earth, had to be there, generating enough gravitational pull to keep those fast-moving outer stars locked in orbit. Rubin repeated this measurement on galaxy after galaxy, more than 70 of them over the following years, and the pattern held every single time. She had not just found a strange anomaly in one galaxy, she had found evidence that most of the mass in the universe was invisible. That invisible mass is what scientists now call dark matter, and Vera Rubin's work in the 1970s remains one of the strongest and most direct pieces of evidence for its existence that we have. Here's what makes this discovery so unsettling once you actually sit with it. Dark matter does not emit light. It does not absorb light. It does not interact with normal matter in any way that our instruments can currently detect, except through gravity. We cannot see it. We cannot photograph it. We cannot hold a piece of it in a laboratory. And yet, according to the best current estimates, it makes up around 85% of all the matter in the universe. Everything you have ever seen, every star, every planet, every galaxy, every human being who has ever lived, all of that ordinary visible matter is a minority. A thin, glowing surface layer sitting on top of something vastly larger and completely invisible. Rubin spent the rest of her career being incredibly careful about how she talked about this discovery. She rarely used the phrase dark matter directly in her early papers, preferring to simply present the data and let the numbers speak for themselves. She never took sole credit either, always crediting Kent Ford and the other astronomers whose independent measurements, using radio telescopes and gravitational lensing, eventually confirmed what her rotation curves had already shown. She died in 2016 at the age of 88, having been elected to the National Academy of Sciences and awarded the National Medal of Science, but never awarded the Nobel Prize that many scientists believe she earned. 3 years after her death, in 2019, the United States government formally renamed a massive telescope project under construction in Chile in her honor. A machine designed in large part to finally answer the question her own research had raised half a century earlier. What exactly is dark matter, and what else is out there in the universe that we still cannot see? Now here is where the story of the observatory itself gets genuinely dramatic, because building this machine was nowhere near as simple as pointing a big mirror at the sky. The project was first proposed in the late 1990s and early 2000s under a different name, the Large Synoptic Survey Telescope, and it took more than 2 decades of design, funding battles, engineering setbacks, and international coordination before it produced a single usable image. Ground was broken on Cerro Pachón in 2015. The mirror itself, a piece of glass 8.4 meters across, had to be cast, cooled, and polished with a precision so exact that even a temperature change of a few degrees during the process could ruin the entire piece. It took years just to shape that mirror correctly. The camera was arguably even harder. Built primarily at the SLAC National Accelerator Laboratory in California, the LSST camera required custom sensors capable of detecting extraordinarily faint light while remaining stable across thousands of exposures a year for a full decade without meaningful degradation. Engineers had to develop new methods of cooling the camera's sensors to extremely low temperatures to reduce electronic noise, because at the level of sensitivity this instrument needed, even the heat generated by its own electronics could interfere with the very faint signals it was trying to detect. Then, just as construction was accelerating, the project ran directly into a global pandemic. In 2020, work on the observatory slowed dramatically, as travel restrictions, supply chain disruptions, and safety protocols delayed shipments of critical components and limited how many engineers could physically be on the mountain at once. A project that was already operating on a tight, decades-long timeline lost months that could not easily be recovered. Costs rose, deadlines shifted, and still, piece by piece, the team kept building. By 2023, the massive camera, the largest digital camera ever constructed for astrophysics, was finally complete and underwent testing at CELAC before being carefully transported to Chile, a journey that itself required specialized shipping containers and constant environmental monitoring to protect components sensitive enough to be damaged by a single hard bump. The total cost of the project ultimately reached roughly $800 million, funded jointly by the United States National Science Foundation and the Department of Energy, an unusual partnership between two federal agencies that do not often fund the same instrument together, reflecting just how broad the scientific ambitions of this observatory actually are. There is one more detail about the construction of this observatory that deserves attention because it explains why the entire project took so long to reach this point. The telescope itself was designed with an unusual 3-mirror system, an arrangement that allows it to capture an extremely wide field of view while still maintaining sharp focus across the entire frame, something that traditional telescope designs simply cannot do at this scale. Most large telescopes are built to zoom in tightly on a single distant object, sacrificing width for depth. Rubin was built to do both at once, to see wide and see deep in the same exposure, and that combination required engineering solutions that had never been attempted at this size before. The dome that houses the telescope also had to be custom designed to rotate quickly and precisely, allowing the observatory to swing from one patch of sky to another and begin a new exposure within seconds, minimizing the dead time between images, so that the survey could actually capture 1,000 exposures in a single night without wasting hours on repositioning. Every one of these systems, the mirror, the camera, the dome, the data pipeline that processes each image within minutes of it being captured, had to be built, tested, and integrated as a single working unit. And any failure in one system threatened to delay the entire project by months. That is the kind of engineering complexity that turned a telescope that was originally proposed in the late 1990s into an instrument that did not produce its first public image until the summer of 2025. And then, in June of 2025, after more than 2 decades of construction, delays, and engineering problems solved one at a time, the Vera C. Rubin Observatory released its first images to the public. What came back stopped astronomers in their tracks. One image, built from 678 separate exposures stacked together over roughly 7 hours of observing time, showed the Trifid and Lagoon nebulae, 2 enormous stellar nurseries several thousand light years from Earth, glowing in vivid pink and orange detail that had never been captured at this scale or clarity before. Another image, nicknamed the Cosmic Treasure Chest by the team that produced it, revealed that patches of sky that look completely empty to the naked eye are actually teeming with millions of galaxies stacked behind each other in layers reaching back toward the beginning of the observable universe. Claire Higgs, one of the observatory's science leads, pointed out something that captured exactly why this instrument matters so much. If you zoom into one of the faint, fuzzy blobs scattered across these images, you might genuinely be the first human being in history to ever pay attention to that specific galaxy. Not because nobody could technically see it before, but because no instrument had ever been capable of capturing it clearly enough, and no survey had ever systematically looked at that exact patch of sky with this level of depth. Alongside the nebulae and the galaxies, the observatory's very first test images, captured during preliminary engineering runs, had already picked up more than 2,000 previously unknown asteroids, including near-Earth objects and distant icy bodies out past the orbit of Neptune. This was not even the real survey yet. This was the observatory clearing its throat. The actual 10-year legacy survey of space and time officially began in the summer of 2026, and the numbers coming out of it since then have been almost difficult to believe. On February 24th of this year, the observatory issued its first full batch of real-time scientific alerts, and in a single night, it flagged 800,000 separate events across the sky. Newly detected asteroids, stars whose brightness had suddenly changed, distant galactic nuclei flaring as supermassive black holes at their centers consumed nearby material, supernovae caught in their earliest moments, before the explosion had even reached its peak brightness. All of it distributed to astronomers around the world within about 2 minutes of being detected. And that number, 800,000 alerts in a single night, is expected to climb towards 7 million alerts every single night once the survey reaches full operational speed. Think about what that actually means. 7 million individual changes in the sky, flagged, cataloged, and sent out to the global astronomical community every 24 hours, night after night, for 10 straight years. In the first month and a half of the survey alone, during what scientists called early optimization runs, the observatory discovered more than 11,000 never-before-seen asteroids, including 33 near-Earth objects and 380 trans-Neptunian objects drifting in the frozen outer reaches of our solar system. One of those newly discovered asteroids turned out to be the fastest spinning asteroid larger than 500 meters ever recorded, completing a full rotation in under 2 minutes, a discovery that immediately started reshaping how scientists think about asteroid composition and structural strength, because an object spinning that fast should, by most models, be tearing itself apart. It isn't. Which means something about how these bodies are held together is different from what researchers assumed. If you're finding this as fascinating as I did while putting it together, drop a like on this video right now, because it genuinely helps this kind of deep, research-based content reach more people who would want to see it. Here is the part of this story that connects everything back to Vera Rubin herself, because asteroid counts and pretty nebula photos, as impressive as they are not actually the central mission of this observatory. The central mission is dark matter and its equally mysterious cousin, dark energy. Scientists currently estimate that ordinary matter, everything we can see and touch and build instruments out of, makes up only about 5% of the total content of the universe. Dark matter accounts for roughly 27%. And the remaining 68%, the largest slice by far, is something called dark energy, a mysterious force that appears to be causing the expansion of the universe to accelerate rather than slow down over time. In other words, more than 90% of everything that exists is something we cannot directly see, And much of what we know about it comes from indirect evidence, exactly like the kind Vera Rubin first uncovered in the 1970s. The Rubin Observatory is designed to attack this problem using two main tools. The first is gravitational lensing, a phenomenon predicted by Einstein's general relativity in which massive objects, including invisible clumps of dark matter, bend the light of more distant galaxies as it passes by, distorting their shapes in subtle, measurable ways. By photographing billions of galaxies across the southern sky over and over again for 10 years, and measuring how their light is bent and warped by everything sitting in front of them, scientists can begin to map where dark matter is concentrated throughout the cosmos, essentially building a three-dimensional map of something that cannot be seen directly at all. The second tool is watching how galaxies cluster and move relative to each other across cosmic time, since the pattern of that clustering is shaped by the invisible gravitational scaffolding that dark matter provides. Layer enough of these observations on top of each other, repeated across 10 years and billions of galaxies, and patterns start to emerge that a single snapshot could never reveal. This is precisely why the survey needs to run for an entire decade instead of a single year. Dark matter and dark energy do not announce themselves in one dramatic image. They reveal themselves slowly, through the accumulation of an almost unimaginable amount of data, compared and cross-checked and refined over and over again. And the observatory is already producing results that are reshaping how astronomers understand the deep structure of the cosmos. In early August of this year, the Rubin team released a stunning new deep field image of an area of sky known as the cosmos field, a patch of the heavens that astronomers have studied for years precisely because it happens to contain very few bright foreground stars from our own galaxy, leaving an unusually clear, uncluttered window into the deep universe beyond. The new image, built from hundreds of combined exposures, is a 3.2 gigapixel composite containing more than 500,000 galaxies and 50,000 stars in a single frame. 500,000 galaxies in one image. Astronomers who have studied the cosmos field for years using other telescopes are now saying that Rubin's version reveals structure and detail that simply was not visible before. Fainter galaxies, subtler distortions in their shapes, patterns in how they cluster together that earlier instruments were not sensitive enough to catch. This is the kind of data that directly feeds into the dark matter mapping effort, because every one of those 500,000 galaxies is a data point, a tiny distorted shape whose distortion tells scientists something about the invisible mass sitting between it and Earth. Multiply that single image by the thousands of images this observatory is producing every single week, and you start to understand the sheer scale of the dark matter map that is now slowly being built, one photograph at a time, from a mountaintop in Chile. But dark matter is not the only reason this observatory has scientists genuinely excited right now, because there is another category of object that the Rubin Observatory is uniquely built to catch, and it involves visitors from outside our solar system entirely. In the history of astronomy, humanity has only ever confirmed two interstellar objects passing through our solar system. The first was Oumuamua, discovered in 2017, a strange elongated body that tumbled through our system on a trajectory that made clear it had come from somewhere else entirely, from another star system altogether, flung out into the galaxy long ago and only now happening to drift past us. The second was a comet called Borisov, discovered in 2019, confirmed to be an icy visitor from beyond our solar system as well. Two objects in the entire recorded history of astronomy. Scientists studying the design of the Rubin Observatory believe that number is about to change dramatically. Because of its enormous field of view, its ability to scan the entire visible southern sky every few nights, and its sensitivity to extremely faint, slow-moving objects, researchers project that the observatory could detect dozens of new interstellar objects over the course of its 10-year survey, transforming what has been an almost accidental discovery process into something closer to routine data collection. Every one of those objects would carry information from another star system entirely, chemical signatures, structural clues, physical evidence of how planets and debris form around suns other than our own. Astronomers like Michelle Bannister, who has worked closely with the Rubin Science Collaboration on exactly this question, have described these interstellar wanderers as messages from other planetary systems. Tiny physical envelopes carrying information that no telescope pointed at a distant star could ever directly extract. And there's a more immediate, more personal reason this matters too. The same detection capability that finds interstellar visitors is the capability that finds near-Earth asteroids, the objects whose orbits bring them close enough to our planet that a collision, however unlikely in any given year, remains a real and monitored possibility. Scientists have already identified most of the largest near-Earth objects, the kind that could cause global catastrophe. But the smaller ones, the ones still large enough to devastate a city or region, remain far less thoroughly catalogued. The Rubin Observatory, scanning the sky with a sensitivity and speed no previous instrument has matched, is expected to dramatically accelerate the search for exactly these objects, giving humanity more warning time than we have ever had before if something dangerous is ever found on a collision course. There is also a quieter, stranger frontier that this observatory is uniquely positioned to explore, one that goes beyond cataloging known types of objects entirely. Because Rubin is designed to photograph the same patches of sky over and over again across 10 full years, it will be able to detect things that move too slowly or too faintly for any previous survey to notice, including the possibility of undiscovered planets far beyond Neptune in the cold outer reaches of our own solar system. For years, some astronomers have argued that the unusual, clustered orbits of certain distant, icy objects can only be explained by the gravitational influence of a large, undiscovered planet, sometimes called Planet 9, orbiting far beyond Pluto in a region so dim and distant that no existing telescope has ever definitively confirmed or ruled it out. The Rubin Observatory's combination of extreme sensitivity and full sky repeated coverage makes it one of the best tools ever built for finally settling that question, one way or another, sometime within the coming decade. And beyond our own solar system, the observatory is also expected to dramatically expand the census of what astronomers call transient events, the exploding stars, colliding neutron stars, and flaring black holes that appear briefly and then fade, often within days or even hours. Historically, these events were caught mostly by chance whenever a telescope happened to be pointed at the right patch of sky at the right moment. Rubin removes the element of chance almost entirely because it is now watching nearly the entire visible sky, constantly, automatically, every few nights. Which means these fleeting cosmic events are being caught in their earliest moments far more often than ever before, giving scientists a head start to redirect other telescopes around the world toward the same coordinates before the light fades away for good. Now, let's talk about what is coming next, because this observatory is still only a matter of weeks into what is supposed to be a 10-year mission, and the scale of what lies ahead is almost hard to comprehend. Every 3 to 4 nights, the observatory will have photographed the entire visible southern sky at least once, building up layer after layer of repeated observations across every patch of that hemisphere. Over the full decade, scientists expect the survey to catalog roughly 20 billion galaxies and around 17 billion individual stars within our own galaxy, along with millions of asteroids, comets, and other solar system objects, quadrupling the number of known small bodies in our solar system alone. The alert system, still ramping up toward its full 7 million per night capacity, will eventually be feeding real-time data to astronomers and automated follow-up telescopes around the entire planet, catching supernovae in their first hours, catching gravitational wave events and immediately searching the corresponding patch of sky for a visible counterpart, catching changes in the brightness of stars that might indicate anything from a planet passing in front of them to a black hole quietly consuming a companion star. And underneath all of it, accumulating month after month, year after year, will be the dark matter map, growing larger and more detailed with every additional image, slowly filling in the gravitational scaffolding of the universe that Vera Rubin first glimpsed the shadow of more than 50 years ago while measuring the rotation speed of stars in a single nearby galaxy. Scientists involved with the project have been careful not to promise a single dramatic breakthrough moment, a headline discovery that resolves the dark matter question in an instant. That is not how this kind of science tends to work. Instead, what Rubin is expected to deliver is something arguably more powerful, an accumulation of evidence so large, so consistent, and so statistically overwhelming that it can finally start to distinguish between the competing theories that have divided physicists for decades. Is dark matter made of some undiscovered particle that simply does not interact with light? Or does the mystery point toward something even stranger, a modification to the laws of gravity themselves at the largest cosmic scales? Right now, nobody knows for certain. But for the first time, there is an instrument capable of gathering the kind of data that could actually settle the argument. There is something worth sitting with here, something that connects the coldly technical scale of this machine back to the very human story it began with. Vera Rubin spent decades of her career being underestimated, denied access to major telescopes simply because of her gender, forced to fight for basic professional respect, even as her own data was quietly rewriting the textbook, understanding of what the universe is actually made of. She never sought the spotlight. She let the rotation curves speak for themselves, patiently, methodically, galaxy after galaxy, until the pattern became impossible to dismiss. And now, nearly a decade after her death, an $800 million observatory built with the largest camera ever constructed for astronomy sits on a Chilean mountaintop carrying her name, systematically hunting for the very thing she first found evidence of, using nothing but a spectrograph, a 5-meter telescope, and an enormous amount of patience. There's a kind of quiet justice in that. A woman who was once told she did not belong near a telescope at all now has the most powerful survey telescope on the planet named in her honor, built for the express purpose of finishing the question she spent her life asking. And the question itself remains genuinely, thrillingly unresolved. We know dark matter is there because we can see its gravitational fingerprints everywhere we look, holding galaxies together, bending the light of everything behind it, shaping the large-scale structure of the entire universe. But we still do not know what it actually is. We do not know if it is a particle we simply have not built the right detector to catch yet, or something that will force us to rewrite the fundamental laws of physics themselves. Every image the Rubin Observatory captures, every one of those 1,000 exposures a night, every galaxy among the 20 billion it will eventually catalog, is another small piece of evidence being added to one of the biggest open questions science has ever asked. And unlike a spacecraft sent hurtling out into the void, this observatory is not going anywhere. It is going to sit on that mountain in Chile, opening its enormous eye every clear night for the next decade, patiently building a picture of the universe more detailed than anything that has ever existed before, waiting for the pattern buried inside all that data to finally become impossible to ignore, the same way it did for one determined astronomer measuring the edge of a single spiral galaxy more than 50 years ago. If this story pulled you in the way it pulled me in while researching it, subscribe to this channel and turn on notifications, because the Rubin Observatory is only a few weeks into a 10-year mission. And if the first 2 months are any indication of what's coming, the discoveries from this mountain in Chile are going to keep reshaping what we know about the universe for years. Drop a comment and tell me what surprised you most about this story. And share it with someone who would find this as wild as you just did, because this is one of those quiet scientific stories that deserves a lot more attention than it's currently getting.